In this video, we're going to talk about the group 1, the alkaline metals. You find them here on the far left, of the periodic table. There we go. So, and they've all got one electron in their outer shell. Get rid of that now. Right, so let's have a look. We've got lithium there, which is an electronic structure of 2 in the first shell and then 1 in the second. Sodium, which is 2 and then 8 and then 1. Potassium, which is 2 and then 8 and then 8 and then 1. Okay, now the electronic structures of the other alkaline metals you don't have to know, but an important thing is they've all got 1 electron in their outer shell, and obviously they're going to try and gain noble gas electronic configuration by losing that electron. So in all of their reactions, the alkaline metals are pretty desperate to lose this 1 electron in their outer shell, and in so doing, when they do react, they'll lose it, and they'll form ions. So they'll form ions with a +1 charge: the lithium ion, the sodium ion, and potassium ion. So all of the compounds of the alkaline metals are all ionic, never form covalent compounds. All right. So we need to know about the reaction of these elements with water. Now, you've probably done this at school, it's been demonstrated to you. Alkaline metals are stored under oil. And the reason for that is because they will react with moisture in the air, H2O, and they react with oxygen in the air very rapidly. So they have to be stored in oil if you want to keep them for any length of time. Normally, you've probably done this experiment in the lab. You take it out of the oil, you cut it with a scalpel. They're all very soft. They actually get softer as you go along. Lithium is a little bit hard. Sodium is like cheese, and potassium is like butter. And when you cut them, the surface that you expose is very shiny at first, showing it's like a proper metal. But then that tarnishes very quickly because it reacts with oxygen and moisture in the air as soon as you cut it, and it goes dull. Right, let's have a look at lithium then. So you cut a little piece of lithium and put it, and you usually do it in a trough of water rather than in a beaker. You do it in a trough of water. We'll talk about why that is, why that is done for safety reasons. Very strangely, for metals, they float on water. That's floating on the top, and it will fizz. And if you check the pH of the water becomes alkaline. It becomes like pH 14 by the end of the reaction. Now, if you do it with sodium, sodium is more reactive. It reacts quicker. It melts. It's so reactive, it melts into a little ball, and that whizzes around the surface of the water, and that fizzes again. It's making hydrogen, just like the lithium. And again, you get pH 14. You put an indicator in there. If you do potassium, that also melts into a little ball, and very rapidly, usually, that bursts into flame. And it's a nice, lovely lilac flame. It catches fire. So we can see here you've got a clear trend in reactivity. They get more reactive. And we'll talk about why that is in a minute. But let's look at the equation, what's happening. Let's do sodium. Okay, so this is lithium. That was sodium. This is potassium. You've probably seen all of these in school. The other ones you might have seen in videos of rubidium and cesium. But let's do sodium. Okay, so sodium, right, solid, reacts with water, and it forms hydrogen gas and sodium hydroxide solution. Hydrogen gas, of course, is always H2. Sodium hydroxide, this is what makes it alkaline, okay, because that makes hydroxides, ions in solution, and that's very alkaline. And that's why they call it alkaline metals, because they make alkaline solutions like this. Now, if we want to balance that, we are going to, you can see we've got 3 hydrogens on the right-hand side and only 2 on the left. So I'm going to have to put a 2 in front of the water there. So that means I'm going to have to put a 2 there. Now we're all balanced for hydrogens and oxygens. Just worry about the sodium now. We need to put a 2 there. Now, if you want the equation for lithium or potassium, it's exactly the same because they all react in the same way. They all lose 1 electron. So for I'll just do it for potassium. You wouldn't have to, I'm not going to write it twice, but there's for lithium, but there's potassium, reacts with water. Put that as liquid. Forms potassium hydroxide solution, which is alkali as well, and hydrogen gas. Okay, the reason why you tend to do this in a trough rather than in a beaker is because you make this hydrogen gas here and it gets quite hot, that catches fire and explodes, and it can break the beaker. With the potassium, yeah, you can see it gets so hot the hydrogen does catch fire without doing anything, without even in a large trough. The hydrogen will catch fire and the potassium catches fire. Lithium and sodium, sodium occasionally will catch fire, but lithium will never catch fire. Lithium you could actually do safely in a beaker, and the hydrogen wouldn't catch fire there. Okay, so that's the reaction with water, and it's pretty important there to note that they get more reactive. Now, why does it get more reactive? And there's a good reason for that. Right, if we look at the size of the atoms, right, we've got lithium, which is pretty small. We've got sodium, which is bigger. And I've got potassium, which is bigger still. Now, they all want to lose 1 electron. What's stopping them from losing an electron to some extent is the attraction of the positive nucleus. You've got protons in there. Now it's a little bit easier for potassium to lose its outer electron there, okay, than it is for lithium, because you can see the electron in potassium is further away from the nucleus. So that is why the reactivity increases as you go down the group. And if you looked at the as you go down the group, the reactivity increases. Because it's easier to use that electron. So lithium, sodium, potassium you usually have in school, and you do those. And you can see the trend there. Rubidium and cesium, you don't have them in school usually because they're very expensive, because they're quite rare. But there are a few, like I say, there are a few videos on YouTube and stuff, and you can see rubidium and cesium reacting with water, and it's much more violent than even with potassium. Francium, everyone always says, well, what would francium be like? Well, that presumably would be more violent, even still. It's a very, very rare element. It's estimated there's probably only about 12 grams of francium in the entire Earth's crust, so you're never going to be able to do that as an experiment. Now, on the AQA specification, it also says you need to know the reaction of these elements with water, which we've done, but also with oxygen and with chlorine. So I'll do chlorine first, okay? And this, you might have done this in school. Right, what you do is, if you get a gas jar of chlorine there, and chlorine, of course, is a greeny yellow gas. And here we've got a, this is called a deflagration spoon. It's just called a spoon. And we have got some sodium some sodium metal there. If you put the sodium metal into the chlorine, nothing happens. But if you heat, you've got to set the sodium on fire, first of all. So you put it into a Bunsen flame until it's just burning a little bit. And you plunge it into the gas jar of chlorine. Okay. The yellow color of the chlorine disappears, and this sort of gets all smoky. And what's happened there is you get a very bright light. Okay, so it burns. So the sodium will burn. In the chlorine. You might be able to hear fireworks. in the background here. It's not bonfire night, but it's the 7th of November. But anyway, sodium burns in the chlorine and it produces a very bright orange flame. When that flame dies down, you've got white smoke left over. That white smoke is tiny particles of solid sodium chloride. So the reaction would be Na solid plus CO2 gas goes to Cl. Now, to balance that equation, that's the sodium chloride produces actually a solid. It looks like smoke. Well, it is smoke, but smoke is actually not a gas. It's tiny particles of solid. So to balance that, chlorine is diatomic, of course, Cl2. So I've got to put a 2 there and a 2 there. That's balanced. Now, if you react it with lithium or with potassium, you get exactly the same reaction. The equation balances in the same way. I do lithium, you burn it lithium in that, you'll get lithium chloride. Balance that in the same way, and you get white smoke of lithium chloride. Exactly the same for potassium as well. Just before we finish then, so it does say you've got to say how they would react with oxygen. Well, they all react in the same way. They won't react with oxygen that quickly unless you heat them. They tarnish very quickly in air, but I think it's reacting with the moisture in the air. But if you set fire to it, it will react with oxygen. So let's do sodium. Sodium, solid, reacts with oxygen, which is of course O2, and it forms sodium oxide. That's the formula of sodium oxide, which is a solid. So to balance that, we have to put a 2 there, the oxygens, and then we need 4 sodiums. Let's say lithium and potassium are going to be exactly the same. Potassium will react a bit more vigorously than the sodium because it's more reactive. Lithium a little less vigorously because it's less reactive, but essentially you get the same sort of reaction. And all the oxides have the same formula, so it's Na2O, K2O, and it will be Li2O also. Okay, so that important thing to remember there. More reactive as you go down the group. Why? Because when they react, they lose an electron, and it is easier to lose an electron as they get bigger because the attractive force of the nucleus is further away. And I also should mention there is something called shielding. Shielding increases as you go down the group. Shielding is the inner shells of electrons here, which I'll just draw there for potassium. They kind of protect, stop the nucleus attracting the outer electron quite as much. They block the attractive force. It's called shielding. So shielding increases as you go down the group as well.